We talk about cosmological evolution of galaxies, and as a last talk, I picked up this place, and Daniela translated it in the... this is actually the place where I like to hike. This is tunnel, one-way tunnel. So I hope to emerge it by the end of my talk. So I will focus in my last talk about the central kiloparsec of galaxies, and I will also talk, well, let me open my cards. I will talk on one hand on dynamical phenomena in the central kiloparsecs, which are the nested bars. And I will emphasize the gaseous nested bars, something that avoided this conference so far, largely. And then I will talk about particular efforts to understand the origin of supermassive black holes. I will not talk about M-sigma correlation. John, it will be all yours. So, the central kiloparsec. Is there any reason to actually separate the central kiloparsec from the rest of the galaxy? There are two approaches here. One is dynamical. Is there a distinct dynamical central kiloparsec? And when I say dynamical, I of course mean the inner Lindblad resonances, one or two or three or more, and by now you already had enough of these resonances. I'm talking about the rotation curve in the central part, the shear, the supermassive black hole there, the bulge sits there, part of the nested bars sit there, and there is, of course, star formation. And then let me immediately tell you on the second point, on the morphology. Some years ago, when we've been looking for understanding where the nested bars like to reside, with Johann Knappen and René Pelletier, we did this simple test by trying to understand the Hubble morphology or Hubble fork when we don't know which galaxy we look upon, and we just look on the central kiloparsec. And although we never published, well, no, actually we said it, but never published a big thing about this, there is absolutely no correlation between large-scale Hubble morphology and the central kiloparsec. So that gives hope that there are some interesting phenomena which happen there and is responsible for this diverging morphology with the rest of the galaxy. Now, I also understand that it sits now deep in your throat that bars and other non-axisymmetric perturbations are driver of the secular evolution, and not only secular but also dynamical evolution of galaxies. And that is spiced by different resonances, and from the last talk it was emphasized, but in the previous talks as well, the nonlinear or chaotic dynamics may take over. I will say a few words about the possible origin of nested bars, their coupling and decoupling that was not emphasized so far, and I will emphasize the universal character of nested bar systems and the angular momentum redistribution in galaxies. This conference started from John emphasizing the angular momentum redistribution, and these are the systems that are most suitable or the designer of this universe probably thought about the angular momentum redistribution while allowing for nested bars to happen. And then I will talk, in the second part of my talk, I will talk about the origin of supermassive black holes, and I will emphasize the monolithic versus hierarchical formation of this object. So I will mention the population Swiss stars as possible precursors of supermassive black holes, and then go to the alternative mechanisms. So the bar paradigm, I will just use one slide to summarize what was said, what people said before. Okay, you have nicely axisymmetrically produced disks, maybe, and then something happens which we call spontaneous symmetry breaking, and we get these bars on different scales. Bars substantially change the disk morphology. Remember that the origin of the Hubble fork is that recognition that bars are important. But bars themselves are only first stage in dynamical or maybe secular instability that changes otherwise axisymmetric disks. Bars themselves are subject to numerous instabilities, and maybe the most discussed is the vertical buckling instability that was analyzed in this conference. What I must mention, the different stages of the vertical buckling instability, although I have no doubts that the morphology of the edge-on galaxy is clearly related to all these boxy and peanut bulges, but there is this essential stage of the vertical bar instability where the galaxy becomes asymmetric with respect to the to its equatorial plane, and these galaxies are not yet detected, although the time scale for this asymmetry is at least about 1 gigayear. So I never heard anybody claim and never saw a galaxy which is asymmetric with respect to the equatorial plane in this sense. Now, I do want, although this instability was discussed here, but what I want to emphasize is that this instability is not one-time instability. We have a recurrent vertical buckling, and Inma Martinez did her PhD partly on this, and I would like to show the movie that was done a few years ago, and where we been astonished to discover that, in fact, it is not one-time accident. And so what you will see in the movie in a moment is a bar of a disk edge-on. A bar, you will be sitting in the frame, rotating with the bar in such a way that bar will be perpendicular. Stop to move, but it is perpendicular to your line of sight. And so you will be looking along the minor axis of the bar. And so as the disk starts axisymmetric, the disk is thin, and there is no bar which develops, becomes very strong, as you see from this. No, you will not see it from here, but perfectly symmetric. And then the buckling occurs, and there is this stage where the galaxy is asymmetric with respect to the equatorial plane. This is this Fourier amplitude, A1, Z, and the amplitude may be quite large, as you see from here, which is like 8% asymmetry. And then it goes into symmetric state, and then when you would like nicely to switch off the movie, something else starts to happen, which I would not call really a dynamical instability, but it is related. It's somewhere in between dynamical and secular instability, although that may be heresy to some ears, including mine. Now, the instability develops in such a way that, again, you have a slow break of the vertical symmetry, and maybe I should go now to the movie. Looks like I clicked, and it will work. And so what you see is, first, what I told you, that the bar will be perpendicular to your line of sight. And that is the disk with, if you see, there are the gigayears running here. No. Well, second try. Everybody should get a second try. But maybe I will not touch. This mouse has quite a character. What is going on? This is amazing. Okay, it looks like it's working. Yes. So the first buckling will happen around 1.5 gigayears, which is approximately now. And now, when you are ready that nothing will happen, a slow asymmetry starts to build up. You see it more and more. And then the galaxy recovers its vertical symmetry. Okay, enough of this. Now, this is a conference, not a usual conference, so we need to know whether we learn something about, say, bars. So I have a question to you. What is this? Some wild guess. Everybody except Johann Knappen. Okay. What is this? I mean, it's the same object, that I can tell you. Okay, I think the DJ had a very negative impact on you yesterday. What is this? Okay. Next. You see there is little u there, B, B, R. How much do you need to know the answer? Here's I. Oh. So you see, we need to go all the way to the K-band to really see the object, the bar. Now, which object is this? This is M100, our neighbor. Now, that tells you how difficult it is sometimes to spot. Not sometimes, how difficult it is to spot bars. Okay. If you will remember from this conference, that's just this difficulty, I would be happy. Okay, nested bars. They've been discovered about 60 years ago, Evans saw it first in the NGC 1291, and he mentioned in his paper, which I recently read for the first time, that there is an isophore twist. De Vaucouleurs was more precise. He said that there is a large 10 kiloparsec bar, and there is a 1.8 kiloparsec nuclear bar with 30 degrees misalignment. Then came John Carmody in 79, called them really nuclear bars, and then asked a question, which I answered, is this an oddity of nature? And concluded that most probably we'd talk about triaxial bulges in barred galaxies. Then I confess there was a problem that then like now, to get to particular literature, especially proceedings. They've been not yet on the web. The web didn't exist. And then I had this idea about having it all the way to the center and moving the gas. So the emphasis is on the gas, really. So we have a number of different types of nested bars, and according to their content, they may have different purpose and different dynamics. So the ones that I want to emphasize here are the stellar-stellar, that means outer-inner, stellar-gaseous, and gaseous-gaseous bars that I will emphasize in the last part of my talk, when we'll talk about formation of supermassive black hole. This is NGC 5850, which has, I don't know, I do see a nuclear bar, but in order to emphasize it, I put these arrow bars. And then, you know, the zoo of these objects was growing substantially, and the last review on this subject that mentioned them was that of Carmody and Kennicott, 2004. Now, stellar nested bars at redshift 0 are not unusual objects. About 20 to 30%, rather closer to 30%, have nested bars, I mean, out of these galaxies, all out of total number of these galaxies. And overall, 1/3 of the bar disk have also secondary bars. And by secondary bars, I mean the inner bars, because my understanding is that unlike in numerical simulations, the only way they can form is as a result of the action of large-scale disk, or even beyond. The first survey of nested bars was performed by Line et al. And the sample of 112 galaxies in H-band. Then independently, it was performed by Peter Irwin and Linda Spark. And then Peter Irwin used mainly the Line et al. Catalog in order to get and reanalyze the visual appearance of these systems. And so here are the beasts, and you can pick up your favorite galaxy. There are isophores here, and there are the slightly manipulated images of these galaxies with unsharp masking. So this is just an example. They're quite spectacular, and here is the interesting point, that our neighbor, M31, I'm not even talking about Milky Way, because it was already largely discredited, but M31 is not yet. And so if you look on the nucleus of the M31, it actually may, I say may, because I'm quite skeptical of this, host the smallest nuclear stellar bar. Now, as I promised, I will emphasize the gaseous nuclear bars, and there are plenty of them, and they are quite spectacular. it also is not new that molecular gas likes to live in the center of galaxies, and the $100 question is, how much of this molecular gas is in barred state? So here is an example, NGC 2273, which shows the CO maps superposed on the near-infrared Hubble map of 2273, and includes the velocities in the molecular gas. Another famous example, the IC342, which was exhaustively studied by a number of groups, lately by Mayer and Jim Turner. And here you see the CO contour superposed also on the HST map. Here you can look on molecular gas, not only in CO, and here is another look on the IC342. This is the Owens Valley map with the 4 arcsecond resolution corresponding to 60 parsecs. And there are other guys, don't want to go and to mention, except the fact that in some cases you can measure the actual mass of the nuclear bar, and it may be quite massive, around 10 to the 9 solar masses, which is between 5 to 10% of the dynamical mass within this region. And that's very important. The closest cipher to us, the Circinus galaxy, was also exhaustively studied by Roberto Maialino a few years ago, and also see the molecular gas-dominated inner bar. Okay, well, theoretical perspective. You have a disk, which I didn't plot here. You have the large-scale bar, which spins clockwise, for example. Then you typically have, or you are not obliged, but you have the ILR. And then within the ILR, you can have additional bar, which the most important dynamical characteristic of this guy is that the pattern speed is completely different and higher than that of the large-scale bar. So this is the most interesting point for me. That makes the system dynamical, and I presume if there will be a third edition of Bini and Tremaine, there will be a chapter on nested bars, because it's a very interesting system. Okay. Now, when these bars, misaligned with the nuclear bars, with the outer bars, it is not yet a proof that they have independent pattern speed. In fact, in numerical simulations, we routinely get the inner region almost basically normal, the major axis of the inner part normal to that of the large-scale bar, and the reason is the X2 orbits, which have been exhaustively fed to you in this conference. So that by itself is not a proof of this system being independent dynamical system. Here is the interesting, not exactly theoretical perspective, but can be easily explained by theory, and that is if you plot the bar size versus the size of the disk, galactic disk, you see this beautiful correlation between the bar size and the disk size, and really proving that the nuclear bars are completely indifferent to where they live, in what type of galactic disks. That already tells you that the physical nature of these two guys, or these two families, is quite different. Now, suppose we have the large-scale bar, and we sit in the frame of the large-scale bar, and then something happens in the inner part of the large-scale bar, how can it become independent dynamical system? Well, independent, of course, in quotation mark, because the most important part is that the nuclear bars do talk to the outer bars, to the large-scale bars, and vice versa. They are very much aware of each other. So one possibility that was discussed in a couple of days ago was that you increase the central mass concentration, so the omega minus kappa over 2 curve moves up, and the decoupling happens. How it happens, I will show in the animation. Of course, the crucial point in redistributing mass in a galaxy comes from the gas. Gas is normally dynamically unimportant on the large, if you look on the disk itself, it's usually, at least at low redshifts, it's less than 10% of the disk mass. But the gas has this ability of dramatically respond to perturbations, internal or external, and just to go where we expect it to go, to the center of galaxies, and reach dynamical importance not because its mass dominates the stellar mass or any other mass there, but because it is dynamically cold compared to the stellar fluid, for example. So how can we reach it? Well, we can have large-scale bar, which moves the gas inwards, but we can also have mergers, right? And I wrote here wet mergers, but not obliged. If the host galaxy has enough gas, I don't care about the dry mergers. The effect of the gravitational torques will be the same, moving gas inwards. Now, the importance of the inner Lindblad resonance cannot be overstated, because once the gas crosses the inner Lindblad resonance, the response of the gas, the orientation of the orbits, will be detrimental to the large-scale bar. It will be normal, but not yet decoupled. Only when the mass of the cold gas in the inner parts is sufficiently high, typically around 10%, the decoupling will happen. And the subsequent evolution of this gas is very interesting, but it is not yet conclusive. It definitely feeds the nuclear starburst, but whether it can cascade down to the region dominated by the central black hole is a big question. Okay? What are the other options? Well, the other options for nested bars was that inner and outer bars are stellar bars, and clearly in this case, where you don't have much dissipation, this may be long-lived entities. So even in such a system, the central concentration in the galaxy, in the disk, can increase somewhere by a factor of 2, which will have an effect on the pattern speed, or not only of the inner bar, but also of the outer bar. But what is essential in any case, and that's normally, my understanding is that the right column is the numerical artifact. You can always create initial conditions in such a way that the system will decouple. But in reality, you always need a dissipative component for this to happen. So I said that is for our entertainment on the right, and this is for nature entertainment on the left. Well, there is one galaxy so far where we know for sure, or we think we know, that the pattern speeds are different, and the IIC has has contributed in this respect, as you see from the names. I would like to go now to numerical modeling of the decoupling. And what you see here is a result of such a modeling. When the large-scale bar is stellar, we don't care what it is, but the inner part is gaseous. And so what you see here is the evolution of both the shape of the bar, and here is the ellipticity of the inner bar. You see that initially, well, didn't plot the points here, but it starts with purely axisymmetric disk. Then the outer bar develops, then the gas moves in, and slowly as it accumulates inside the inner Lindblad resonance, the ellipticity grows. The interesting part starts when it is above some critical value. Then what happens after this is probably unavoidable. It reaches the maximal ellipticity, which you will see in the animation, and then the ellipticity goes down. So part of this going down is real, but the last part is probably numerical, because we have really finite resolution numerical simulations always, and because the system seems to be or seems to want to collapse to the center, which gives us hope that something interesting will happen there. On the other hand, we have the size of the secondary bar, which reaches its maximum when the ellipticity is maximal, and then abruptly goes down, and it looks like an avalanche, really. Those of you who skied knows that what is avalanche. How do we know that this corresponds to a decoupling? The horizontal line is the large-scale bar pattern speed, and the curved line is that of the secondary bar. You see initially it wobbles, then it actually moves backward a little bit, not for a long time, but you will clearly see it in the animation, and then the abrupt decoupling. And then the stabilization here is purely numerical effect of the finite resolution in the system. Okay? Now, what happens before we see the animation? I told you that these guys, the outer bar and the inner bar, know about each other, which means they know about the mutual orientation. So here is the specific angular momentum of the inner bar, which starts to decrease once the bar forms, and then starts to oscillate. And these oscillations are clearly in tandem with the orientation with respect to the large-scale bar. The angular momentum the specific angular momentum is maximal when the bars are normal, and minimal when they are misaligned at when they are aligned at 0 degrees with each other. Now, what about the ellipticity of the inner bar? Again, it is growing, reaches the maximum, and then nicely oscillates again in tandem with the orientation to the large-scale bar. The angle between the bars, I really should make it monotonic, but because I kind of presume that I will run out of the screen, divide it here, and so this line is really monotonically decreasing. Okay, so that tells you that decoupling is once it happens, the bars don't couple again. Okay, gas. We talk about the inner gaseous bar. What about the inflow of the gas? So across the inner kiloparsec, this is the curve which depicts the inflow rate, and there is a small flash here because the bar is approximately 1 kiloparsec. itself. But once you go to the inner 600 parsecs, you see that the splash is larger. And when you go to the inner 175 parsecs, then it becomes very interesting, because this rate is in the solar mass per year, and it is comparable to what you would like to feed to central supermassive black hole. Well, that is the linear orbit diagram. I don't think I will be focusing on this, because you saw it many times, except that here is the primary bar, here is the omega of the rotation omega of the disk, and here is omega minus kappa over 2, and you see as the decoupling happens, originally the secondary bar sits here, then it moves here and gradually up to the top. And if this is a stellar bar, it will sit in the particular, there will be a particular ratio of omegas achieved. If this is a gaseous bar, only the sky is the limit of black hole. Okay. Now, this is I want you to show the simulation, and this is just a snapshot from the simulation. The colors are colors of surface density, and this is just the inner 1 point something kiloparsec of the galaxy. The large scale bar is horizontal here and rotates. We will sit in the frame of the large scale bar, and so the rotation within this region will be counterclockwise. So you will see initially starting from axisymmetric state, and then the inner bar developing and decoupling. The movie is a little bit jittery because I transferred it over the weekend, and I guess it was not a perfect transfer. Okay, so what you see, the inner 2 kiloparsec of a galaxy with the horizontal bar, with the large scale bar being horizontal, and here the inner bar starts to develop. You see the large-scale shocks, M=2, coming in and feeding the gas across the inner limb of resonance, which develops as well here. You already see a nuclear bar, not yet decoupled. And now the self-gravity in the gas becomes important. You see that the flow becomes clumpy. The bar grows to such an extent that destroys the nuclear ring, and that feeds additional mass into the bar. Not yet decoupling. Leading shocks can be seen inside the nuclear bar and then disappear. And now the avalanche starts. And if you remember a few minutes ago, I mentioned that initial swing is it goes to the opposite direction of the flow, and now it decouples into the forward direction. There's very substantial time resolution in the simulation because we really wanted to see the details. As a result, the rotation of the nuclear bar is quite slow. But by this time, it collapsed by a factor of 7-8 compared to its original size, and the pattern speed went up accordingly. Okay, I guess we can go forward. Now, what about the gas flow across the interface between the bars. We have measured the gas flow within 40 plus minus 45 degrees to the major axis of the bar, and that is the upper part, quite a jittery influx, okay, and 45 plus minus 45 degrees with respect to the minor axis, and the thick line is the average. So it's clearly a chaotic inflow. To Fourier analyze this chaotic inflow, we produce this power versus frequency, and you see that despite this chaotic behavior, most of the power sits in this particular bit frequency, which exactly can be predicted theoretically. So the bars do know about each other. One of the last comments about this system is when we talk about the large-scale bars, we see these offset dust lanes, which correspond to shocks, as was repeated here at this conference. But when we talk about the nuclear bars, the motion, the gas motion, is much more chaotic. Especially if the bar is large, sits close to the ILR, and as a result, there is a dissipation throughout the bar. The shocks cannot form, and one should not expect dust lanes, but rather a quick collapse of the gas to the inner part of the bar. That basically emphasizes again that most of dissipation is in the dark pixels are in the outer part of the nuclear bar that changes as a function of the orientation between the outer and inner bar. So the gas dynamics in the outer bar and the inner bar completely different. I don't think I have time to talk about the orbital structure of nested bars and introducing the loops. It's a very interesting way to analyze, to quantify the behavior of these guys. But what I want to answer is this question: how long-lived are these systems? And I can tell you that under certain conditions, and especially when the gas is not important, they can live a Hubble time and maybe even more. So to analyze this, under what conditions the nested bars will be long-lived, we did analyze them using the Lyapunov exponents. That is a measure to analyze the chaos in the system in the way that if you take a chaos is dynamical instability, it may be also secular instability, depending on the time scale, of course. So we take two orbits which are starting from nearly identical initial conditions, and if they diverge as a function of time exponentially from each other, we would mean that such orbits are chaotic. And system which is populated mostly with such orbits will be a chaotic system. What you see here is the Lyapunov map of the nested bar system. In the x-axis, we have just the radius, the radial distance to the central rotation axis. In kiloparsecs, in the vertical axis, you have the rotational speed, and the dark regions in the left column correspond to chaotically unstable system which has a chaos which develops in a very short time. The white colors are, on the other hand, represent the regions which are stable, and you see that the inner part, let's see the middle line here, the middle snapshots. The inner bar sits here, and the outer bar sits in the rest of the system. So you see, because there is a ILR between them, there is a lot of chaos here, but that is actually healthy. Systems with a certain degree of chaos are quite healthy, and the problem starts when you increase the amount of chaos, so you change the mass ratio between the bars up or down, and then there is either no place in the phase space for the nuclear bar, so it dissolves, or there is, if the nuclear bar becomes very massive, as you see here in the bottom, the outer bar dissolves. I don't have time to go too much into this, but what I want to mention, that the system of nested bars represented by this, by the molecular or stellar inner bars and stellar outer bars, is not unique. In fact, the system of triaxial halo and large-scale bar is very interesting and possesses some interesting similarities, although dynamically this is not the same system, and that is, of course, because the triaxial halo figure is nearly non-rotating. Orbital structure, well, just to conclude about the nested bars mechanism, they live indefinitely numerically, and under certain conditions they probably live indefinitely in nature as well, unless the dissipation is large. I don't have time to talk about the relationship between the inner nuclear molecular bars and the AGNs, but there is this question: why don't we see clearly correlation between the nested bar systems and AGN activity? And I wanted to answer this by bringing this small animation telling you or describing basically that there is a clear mismatch in the time scales between the feeding process on the larger scales and the accretion processes around the black holes, and to correlate them is really a challenge. And we have still problems having sufficient resolution at small scales. Now, that brings us naturally to the supermassive black holes at the center of galaxies. It's indisputable that the feedback from both dynamical, radiative feedback from the supermassive black holes can have potentially a dramatic effect on the rest of the galaxy. Although already I expressed my opinion that the way we treat it now is not probably the proper way, by considering the central black hole being just a giant orby star. There are two views on the origin of the black holes. One is, the picture speaks for itself, okay, and so I will try to address one of these ways. There's no question also that the supermassive black holes originate very early in this universe. Specifically, the last detected quasar is sitting at above redshift 7. And this is probably only the tip of the iceberg. There is quite a population of guys that sit between redshift 6 and 7 and between 5 and 6. So one can actually make some conclusions, and unfortunately, again, I will focus on the dynamics rather than on these conclusions. Most importantly, these guys are ubiquitous, right? They are everywhere The universe is infested with supermassive black holes, and I don't need, if I would talk about this few years ago, that I would probably spend half of my talk on trying to prove this point, but now it's common wisdom. Then it's also common wisdom now that black holes form at high redshifts. However, it's a challenge for a hierarchical model of structure formation in this universe, how to form them so massive and so early. There are two ways we can estimate the mass of the supermassive black holes: gas dynamics, stellar dynamics. I presume that John will talk about this, and again, this is not the subject that I want to focus. Black holes can grow through accretion process, and this accretion process can be, the formalism is quite simple. M dot that we will be using depends on the mass of the black hole, on the density of the environment, and on the temperature of the environment, okay? And that is just a simple spherically symmetric Bondi accretion rate, and although it probably never happens around black holes, but it gives us some feelings of, intuitive feelings of how it goes. Now, what are the options to produce these black hole seeds? The most popular and pushed option today, these are descendants of population 3 stars. The black holes, in this case, can be seeded above redshift 20. The problem, however, as we will see, is that these seeds are small, of the order of hundreds of solar masses. The other possibility is rather a monolithic direct collapse to a sizable size and mass black hole. Now, how can this happen? And these are the most general statements, because we are only in the beginning of understanding how this thing proceeds. At some point, when population 3 stars form and then die, the universe is made out of small dark matter halos that have a mass of less than 10 to the 8 solar masses, and therefore the virial temperature less than 10 to the 4 degrees. H2 has difficulties to form, and therefore the gas has difficulty to cool below the floor of the atomic H1 gas. When you bring these two systems together, it's clear that a gas that has a temperature of less than 10 to the 4 degrees, of about 10 to the 4 degrees, but not less, cannot concentrate, cannot be trapped by dark matter halos of 10 to the 8 solar masses, whose virial temperature is exactly 10 to the 4 degrees. So the trapping must happen when the dark matter halos grow in mass and the temperature goes above 10 to the 4 degrees, and so the gas can cool and fall into the halos. Now that brings two interesting characteristic masses. The virial mass of 10 to the 8 solar masses of dark matter, and the fraction, the universal fraction of baryons, which tells you that in these objects, the maximal mass of the black hole forming cannot exceed 10 to the 6 or 10 to the 7, let's say, liberally. If, however, the gas is enriched, heavily enriched by metals, the black hole seeds will be smaller because they can cool down below 10 to the 4 degrees and therefore will collapse into slightly smaller halos. Well, I will talk about assuming that the enrichment process is really non-effective. Now, what are the population 3 seeds? Well, they need to grow from, say, redshift about 20 to redshift 6 when we see already 10 to the 9 solar masses black holes. If they grow maximally at the Eddington rate, the E-folding time of saltpeter is just above 440 million years. This is not bad, but if you want really to grow to above 10 to the 9 solar masses, it will take you 3 gigayears. Now we see the quasars already at redshift 7, 6. So we need to increase the efficiency. There's clearly a problem with growing them so fast, so massive. One can say, oh, maybe they grow faster through the mergers. But then the problem is when the mergers are very efficient, and too many of them happen every morning, then there is this slingshot effect. And the mass starts to be ejected from the system. This is good. It also will produce the accretion cutoff. On the other hand, if we take a view of a monolithic direct collapse, then the growth happens somewhere between starting from redshift 12 to 20, okay, but that's where the first 10 to the 8 solar mass dark matter halos appear, and down to the redshift 6. So you don't need too many mergers at all here. There is a problem which I would like to address. How much time more I have, by the way? 1 more hour? Well, when did I start? I started 35 minutes ago, right? Okay, 18 minutes. Okay. So what is the problem? The problem is if you want to make the black hole in one run, one can argue you will form a self-gravitating gas, and the self-gravitating gas will fragment and form stars. Many stars means small black holes. This is not what we mean, right? Because we cannot get rid of these guys after this. We want one big sink rather than many small guys. So what is let's take a look at this. Suppose we have the accretion rate on the supermassive, we include the case when there is no seed black hole, just a self-gravitating cloud. So in this case, M and this black dot, which is a white dot really, that means the mass of the black hole. And if you don't have it, if there is no seed black hole, then this is still applicable. I wrote it in a more general case. Okay, so that is the maximal accretion rate that you can think about. Okay, and it is rather small, 10 to the 4 solar masses per year if we talk about 100-degree molecular gas. So using this particular estimate, let's look on different cases. Stellar collapse. In the stellar collapse, if the gas is around 10 to 100 Kelvin, you get very small accretion rates, and that will limit the size of your black hole, the mass of your black hole. In the population 3 case, the gas is slightly hotter because it has difficulty to cool down, so say 1,000 degrees, so we get 10 to the minus 2 to 10 to the minus 4 solar masses per year rate. And then in the direct collapse, when you have 10 to the 4 degrees, you get to 0.1 solar mass per year. Now, what I will argue is that there is not only quantitative difference along this sequence, but also qualitative difference, how the gas, large accretion rates behave differently than the other guys. The main problem, of course, that we cannot deal with the spherical collapse. We cannot deal because this universe was created, no, it was not created with angular momentum, but it developed it in the linear stage. And even 1% of the Keplerian support would mean that the gas will stop very quickly. And so we immediately discard the spherical collapse. But during these 2 weeks, we discussed the spin of dark matter halos, right? And we know that this is what happens. And so when it happens, the gas develops non-axisymmetry. The system is not axisymmetric. The large-scale dark matter halos are triaxial, universally triaxial, and that is very efficient way or initial conditions to extract angular momentum from collapsing gas. Okay? So how does it go? How do gaseous bars develop? I must say that dealing with gaseous bars is easier than to deal with stellar bars. For a simple reason, you can have an equation of state and certain things can be done analytically, or at least the physics is understood. And I would like to emphasize this Maclaurin ellipsoid sequence, which is basically the angular momentum sequence. So you start with a low angular momentum here, and you increase it from left to the right. And what happens there is quite counterintuitive in the sense that you would expect that if you take the drop of water and start to spin it up and up, it will flatten more and more, and somewhere here you will get a disk. Nature, however, has sideways, and that means that it can break symmetry spontaneously. And you have all this nice sequence of non-axisymmetric features or objects, each of them having a different internal and external dynamics. Some have internal circulation, some figure rotation. A figure is not rotating. In the other cases, you have both internal rotation and figure rotation. And so it's a very rich family. Why do I bring it up? Because of the following thing, that we don't know, even when we talk about the gaseous bars, what they correspond to in the sequence of the one that I showed you before. There are some suspicions, but the theory clearly is lagging here behind numerical simulations. So, however, we do know from numerical simulations when the bar instability in the fluid systems develops. And I want to stress that I'm talking about fluid systems, not stellar dynamical systems. So the critical value, one can define a parameter alpha, which is the ratio of the cold kinetic energy and the potential energy of the system, and the ratio between the omega, the rotational omega, and the Jeans frequency here. And without going into details, there is a clear critical value for this parameter, above which the system goes into global instability. Here is the result of numerical simulations by Weiss et al., which looked on the collapse of the gaseous component into pre-existing dark matter halo, which has the NFW profile. So what you see is that it's a time sequence where you have the density profile, log density profile versus the log radius. And initially, you start with uniform system, uniform density, and then you get to the point where the system starts to develop dynamical collapse. And basically, the profile is that of the isothermal sphere. The gas here can cool down below 10 to the 4 degrees, but it doesn't do this. Okay? And the collapse goes isothermal. Here is the evolution of this alpha parameter that I just discussed versus the enclosed gas mass in the system. So what you see here, and I would like to emphasize the upper horizontal line, which is the line of the dynamical instability. And you see what happens in the gas, where we measure the alpha parameter. The parameter periodically goes above the instability limit, and that means that there is spontaneous break of the symmetry, of the axial symmetry in the system, and the gravitational torques start to extract the angular momentum from the system. Another interesting point is that the system goes supersonic. So the inflow velocities here are about Mach 3, and that will be important later if I get to the point. Here is the interesting correction to the, that's including the questions. Here is the interesting correction to the tumorous instability. You saw this dispersion relationship here. It is for razor-thin disk, gaseous disk, where this is the stress density, that's the wavelength, or 1 over wavelength, and this is the, ignore the T, this is the sonic velocity, the thermal velocity in the gas, and that's the epicyclic frequency. Such a disk is unstable to fragmentation if the surface density is above critical one. And so razor-thin disks live in the danger of forming stars. However, if you make these disks turbulent and you have a way to support this turbulence, they will not be any more geometrically thin, and you see this that how it affects the dispersion relationship. H is the thickness of the disk, and when H is increasing, the destabilizing character of the gravity disappears, and so one should not expect fragmentation in such disk. Why it is important? It is important that the gas collapsing to the center, if it develops turbulence, it will follow a particular evolution, and that means that, from the left to the right, is the rotational velocity of the infalling gas is increasing. As it moves from the left to the right, it first encounters this vertical line, which is the critical global instability for spontaneous break of the axial symmetry. And from here to the right, the system will be subject to gravitational torques and will lose the angular momentum like crazy. While the fragmentation sits here and is quite separated from the region of the global instability. So this is local instability, this is global instability. And what I wanted to emphasize only is that the collapsing gas will, if the turbulence develops there, will first encounter the global instability, and only later, if at all, they will fragment. And remember that fragmentation is the thing that we want to avoid. We want to form massive black hole instead of forming many mini black holes and stars, which pollute the universe. Now, the turbulence. What drives the turbulence? Well, the gravitational collapse drives the turbulence. So you start with low angular momentum gas at large distances, say a few kiloparsecs. That's the size of this dark matter halos with a mass of 10 to the 8 solar masses. they quickly go and develop the supersonic virial turbulence. That will make the system stagnate because of this small angular momentum. The moment the system stagnates, the turbulence will decay, because if it doesn't collapse, there is no driver. Once the turbulence decays, it goes into the global instability, because the disk stops to be as fat and becomes more and more subject to instability. But first it's the global instability, so the bars, which will allow the extraction of angular momentum, and after this you have resumption of the gravitational collapse, and that is confirmed by numerical simulations. And then the sink, there is this feedback, and the question is, what stops this vicious circle? Okay? So, what stops this circle, to be short, is that the flow stops to be isothermal. And it stops to be isothermal when it stops to be transparent to its own radiation, and that happens at few tens to few hundred astronomical units. This is how it looks, the turbulent flow. I have no time to discuss the details of supersonic turbulence, and I have no time to discuss the importance of the Larsen relation. But what I want to show here is that when the gas becomes self-gravitating and decides to go into collapse, and you would expect these tips of the iceberg where the stars will form, it's not the gravity alone which decides which stars form, but it's the gravity together with turbulence. And if turbulence is at this level, only in few places there will be fragmentation. If turbulence will be higher, the gas will not fragment at all. Okay? So, I talked in the beginning of previous week about this log normal distribution. The density fluctuations in the turbulent medium have this type of distribution. And one can actually calculate what fraction of these density perturbations will be genes unstable. And an interesting point that I want to make is when you calculate this fraction of the guys that will collapse and fragment and form stars, the lower limit of this integral depends on the Mach number. And once the Mach number becomes large, this fraction goes very low. So the fragmentation can be avoided. There are two, you're like Nemesis. I will skip the details. I will just mention the two alternatives. The one type of the collapse is when the angular momentum is unimportant. And then the object that you get at the center will be a quasistar, a massive object of 10 to the 6 solar masses that develops thermonuclear reactions. That is one view which was recently explored by Begelman, Voluntary, and Martin Rees. I will not go into details because Johan will not drive me to the airport, right? But instead, and I will not discuss how this thing collapses to the black hole, but instead I will emphasize the alternative. And that is when the angular momentum is important. And that's where you don't probably get this central object which develops thermonuclear reactions, and the timescale for these thermonuclear reactions in 10 to the 6 years, which slows the whole process of star formation, of the whole formation dramatically. Instead of this, you have the dynamical instabilities all the way, and I will almost finish showing you Well, nothing can be seen here. That is a pity. It always comes unexpectedly. But what you see here, what you're supposed to see here, that the system really forms a central object which is dominated by angular momentum. And the torus, thick torus around it, which is dynamically unstable. The evolution of this system is very complex. And in order to address all the physics, you actually need to address a different physics at each characteristic level. Because we start from 10 kiloparsec collapse, and we go to 10 astronomical units. And the system that you see here is the intermediate guy, which we reached at 10 parsecs now. Interesting. Okay, I go to conclusions, and want to emphasize that there are real problems of forming the black holes from the population's recesses. There's simply not enough time. And although the direct monolithic collapse is not very popular these days, but in fact it may be resurrected for these cases. It naturally explains the apparent cutoff in the black hole masses at 10 to the 6 solar masses black holes. So far, although there have been incredible attempts to find the intermediate mass black holes, they are not found. And the reason for this may be that the process that I just explained in some details. There is a way to avoid forming massive objects which go into the stage of nuclear burning in the center of galaxies and then form smaller mass black holes. And the way to avoid it is proper treatment of the fact, and that has some corollaries to the feedback of AGNs, that the feedback from black holes, unlike the feedback from stellar evolution, is heavily anisotropic. Black holes know that there is a preferential way to release its energy and angular momentum in such a way that they can coexist with the galaxies without destroying the interstellar medium there. And I'm finished.
Question? Anybody? One short question.
Yes, Katrin.
So, I might have a riddle for you.
Riddle? This is exactly what I need.
So, I have observed a galaxy in the Atlas 3D sample that has no signs of interaction and has 10 to the 9 solar masses of molecular gas in the central 100 parsecs. And what we see is that the AGN at that level does an extremely good job clearing the gas out when the gas is very close. I was wondering if you had any ideas how gas could get there without leaving any sign of interaction or H1.
Well, all what you said doesn't convince me that AGN is so efficient. I mean, the gas is, after all, there.
It's coming out at about 200 solar masses per year is the molecular outflow.
Well, there are many ways to explain this. The gas could get there before the AGN phase. But the thing that I probably should talk, but didn't have time to talk, is that this change of the paradigm. You all know about this molecular tori in the AGN, type 2. It was... They've been designed in 1986, 88 as being in hydrostatic support and sitting there just to obscure nice view of AGN to all of us. So most of them, like CIFAR-2 galaxies, we don't see the direct environment of the black hole. But in reality, the theorists never explained how that such a torus can be in hydrostatic support. And the shift of the paradigm is that it is probably not in the hydrostatic support, but this is part of the molecular, maybe hydromagnetic wind that is driven by the rotation of the molecular disk, and the molecular gas just slides along the magnetic lines like bits on the wire. So what you're saying is actually not only limited to this particular galaxy. It may be that all molecular tori are just these hydromagnetic winds around the supermassive black holes in all Cipher-2 and Quasar-2 objects, and the part, the obscuring part, is simply the base of the wind where the optical depth is sufficient. So this, what you're saying, is a nature of, is apparently a widespread phenomenon. Not everybody is aware of it.
Thank you again, Isaac, for 4 beautiful lectures.